Welcome everyone, and for presenting my mentee, I would like to thank you to everyone who contributed to this event we have. My mentee Hatice, she is a student in the Department of Computer Engineering, and with her we studied the graph theory with probability, and she will give a talk entitled as Probabilistic on graphs.
Hello everyone, today I will talk about probabilistic method on graphs, and I will start with some requirements. These preliminary notions will help us to understand theorems, and then I will move on to existence and expectation. Here we will learn about some probabilistic ideas, and then I will move on to alteration method. Let's begin with the graph definition. So as you can see, a graph G is a triple consisting of a vertex set, an edge set, and a relation that associates with each edge two vertices called as endpoints. This is one of the famous examples of graph theory. We can model this bridges of Königsberg problem as a graph, and we have some areas. This is X, this is Y, and this is Z, and there is a W, and we will represent these areas as vertices, and these bridges are the edges between these vertices. And we will start with this definition, and then we will move on to clique and independent set. A clique number in a graph is a set of pairwise adjacent vertices. They are connected. An independent set in a graph is a set of pairwise non-adjacent vertices. And these vertices forms an independent set, and these red ones forms a clique set of a graph. And also, the degree of a vertex V is the number of incident edges to vertex V. So, for an example, this one has a degree of 4. A complete graph. So this is an example of a complete graph. So you can think it as like all vertices are adjacent to each other, as you can see, and meaning there is a direct connection between every pair of vertices. And this is important for our Ramsey theorem and Ramsey number. So in Ramsey theory, the main problem in Ramsey theory is what is the minimum number n such that when we color the edges of a complete graph K sub n with red and blue, we are guaranteed to have a red K sub S and or a blue K sub T. We denote this number by R of S and T, and we can model the following example with the idea of this theory. Let's say in a group of 6 people, there are either 3 of them who all know each other or all strangers to each other. And we represent this as with the Ramsey number R of 3 and 3. This is equal to 6. On this graph, so we say if we are able to say the statement, we need at least 6 people. So think about the reverse one. If we have at most 5 people, for example, if we have 5 people, we can't say there are 3 of them who all know each other or all strangers to each other, because we can form all red triangle or all blue triangle. That's why we need at least 6 people. And then we have another definition. This is dominating sets. So think about this as we want to observe all the vertices on the graph in a sense of reachability. How do we do that? First, choose a random vertex. Now we can observe all the vertices adjacent to the chosen vertex. Then beside the chosen vertex and its neighbors, choose another vertex that is out of observation. By doing this, these chosen vertices will form a set, and this is called dominating set. The rectangle squared ones also forms a dominating set, and the circle ones are also forms a dominating set. And then we can talk about the probabilistic part. And I will begin with the existence part. We can explain existence by assuming we want to prove the existence of an object with some desired property. Then define a probability space where the incident of the desired property is an event A. If this event A has a positive probability, then the desired object exists. And theorem says that if this number is less than 1, then the Ramsey number is greater than n. Okay, using the idea of existence, let each edge appear independently with probability 1/2 with the vertex and on graphs. Then, if the probability of the event Q is positive, then the desired graph exists. Use the notion here. And we define Q as no peak-leaf or independent P set. Each possible peak-leaf occurs with probability of this number, since obtaining a complete graph requires processing all its edges and they occur independently. Thus, the probability of having at least one peak-leaf is bounded by this number, and this bound also holds for independent sets, P sets. Therefore, the probability of not Q is bounded by 2 times this number. If this number is less than 1, means the probability of Q naught is less than 1, then it is guaranteed that probability of Q is greater than 0. Expectation part. The random variable is a function that simply assigns values to the elements of the current probability space. And the expectation of a random variable X is the weighted average of X. And another property of expectation is the pigeonhole property. And it says that there exists an element of the probability space for which the value of X is as large as or as small as its expectation. Applying this property requires a value or bound for expectation. We will use this property to and we have an important lemma here. This is linearity property. And by this, we can say that expectation is a linear function because we can take the constant outside of this function. And also, we can interchange the summation and the expectation function. Indicator variables as a remarkable power here too. When we make these variables text values either 0 or 1, they are called indicator variables. The expectation of an indicator variable is the probability that it equals 1. And we often use this lemma when we have random variables that come substructures. This kind of random variables is some of variables indicating whether one of the possible things being counted actually occurs. And these properties is one of the first use of probabilistic method. So we can begin with the alteration method. The notion of the alteration method is a minor alteration can yield a desired property when a randomly generated object gets close to it. And remark says that there is a lower bound for this. When the degree of every vertex of G is K, every vertex dominates K plus 1 versus, including itself. So every dominating set has at least this number of vertices. We will use this in theorem too. And also, we have this fundamental inequality, and this is just for the notion. And this is our theorem, and it says every n-vertex graph with minimum degree k greater than 1 has a dominating set of size at most this number. So we will try to reach that number by using alteration method and existence and the other properties that I show. We will begin with choosing a random set A, such that A is a subset of vertex set of G, and include each vertex independently with the probability P. And then let T be the set of vertices that are outside of A and have no neighbor in A. Using the idea of alteration method, set A is altering into A union T by the definition of dominating set. When we calculate the expectation of the size of the A union T, we will know how many vertices we should have at most to configure a dominating set. This is the indicator variable we will be used for the set A. If the vertex V belongs to A, this indicator variable takes the value 1, otherwise 0. And we know that because we choose this, and since each vertex occurs with probability P in A, we have this following statement. Here, we use the linearity property here. We interchange the summation and the expectation function. And then we calculate the probability of the vertex belongs to A. We know that the indicator variables takes the value of 1. And then we know that it's P, probability of these are P. And when we do this for all the vertices in the vertex set, this becomes n times P. For the T sets, let V has at least k neighbors. Using the fundamental inequality, we have the following. Again, we define the indicator variable for the T set. If vertex V belongs to T, we'll take the value 1. And again, we use the linearity property here. We interchange the summation and the expectation functions. Then we use when the indicator variables is equal to 1. Here we have less than or equal to because we said at least k neighbors. So this neighbor number can be greater than k. So we defined the probability for the set vertices in the set A as P. So this will these vertices will have the probability of 1 minus P. And since they have at least k neighbors and including itself, they will have k plus 1. And when we do this for all the vertices in the vertex set, this will become n times this number. And here we use the fundamental inequality. Yes, this part is just that. And therefore, using P equals this number, why did we choose P as this number? Because we are trying to balance. The expected size of the dominating set and the vertices that are not dominated. So we choose this number for the balancing. Then we have the expectation of the size of the union A union T as this, and we know that this is less than or equal to this number. And when we choose P as this number, it will become this many vertices. By the pigeonhole property, we say that there exists a dominating set S such that the size of S is at most this number. Thank you for your patience.